computers. So the first part of the talk will be why do we need to load classical data and what do I mean by this process. The second part of the talk will be more about the interplay between various control parameters that define the energetics of such a process, which allows you to load classical data. So maybe the last talk was quite colorful and with all the music and stuff, so I'll try to match the enthusiasm, maybe not the music. Sorry, I have mine. So this talk was, this work has been done in collaboration with people in Europe, based in Hungary, for instance, and the people in Singapore. So some of these people are based on quantum algorithms and therefore work on optimizing the algorithmic part of any algorithm or finding ways to solve problems. And my part was more on the energetic side, where we try to inject control parameters to see what could be a hardware roadmap for realizing quantum random access memory or accessing classical data coherently in a quantum device. So first, the question is that why do we need to access classical data onto on quantum computers? And this is essential for any task in machine learning where there's copious amounts of data and you need to have a way to load them first, to access the data and then analyze it. And this becomes more important. You will appreciate this more when you see why is quantum random access memory different than, say, a simple phase encoding or an amplitude encoding, where you encode the data itself in the quantum circuit. So this is very important for quantum phase estimation kind of problems, as I will show in an example. And it also works for various other algorithms and has applications in quantum algorithms solving cryptanalysis or cybersecurity. So the device or the circuit that is used for doing this task is called a QRAM, or a quantum random access memory. And now we define the outline of the problem. And the outline is that we have n number of address qubits. That is, we need a certain number of address qubits to say what elements of the memory I want to access. And m is the number of bits per memory element. So I could store more data per memory element, but I restrict myself to having m bits of memory. So a QRAM operation typically means that I provide an input address register, which is given by the subscript a here, and a target register initialized in some state b. And depending on the memory element I that I select, I can perform some kind of control operation on the target register. Now, a simple way to visualize this is by something known as a multiplexer, which is a device which works on 3 address. In this example, works with 3 address bits, and depending on the values of the address bits being 0 or 1, you can either perform a targeted operation after extraction. So the U0 that you see is this operation plus an operation that is based on the classical memory that you've just accessed, and therefore you can perform targeted unitary operations on some other qubit, which is the plus plus here, depending on the extracted value of the classical bit. Now, the question is that where does it become important and how does it differ from simple encoding such as angle encoding or phase encoding and so on. And therefore, I will bring you to an example where I'll abstract out many details. So the question is, how do you calculate the ground state energy of a Hamiltonian H, which is the sum of some Pauli terms with coefficients alpha j. And inside the QPE, so the outer box that you see is a quantum phase estimation algorithm, are 2 main things. The first main thing is the block encoding, which is that how do I operate this unitary operation, which is based on the Hamiltonian, repeatedly on a target system, and how do I do it efficiently? Now, one would say that if I know the Hamiltonian, I would typically make the matrix, store it, and then retrieve it at will and do these operations. But that's not the best way, and that's not the best way because for 200 qubits, for instance, you will have a matrix which is to the power 200 times to the power 200. So I need a better way, and that better way is QRAM. How does it work? Is that I perform a coherent superposition of asking or applying various elements of the Hamiltonian. So I don't just apply Pj conditional on some memory, but I inquire alpha times j, and I directly access all the terms of the Hamiltonian, and I repeatedly apply it in the quantum phase estimation algorithm. So this is different from, say, doing an angle encoding or something similar. So this is an example, and we can calculate the energetics of such a process, of how many times have you queried the memory and so on. But what we'll go into is more on the architecture side. So how does a quantum random access memory work on a real quantum device, and how can we access the energetics of such a operation? So a multiplexer, the circuit that I showed you before, has a circuit depth that scales exponentially with n, and therefore the infidelity also, because the errors accumulate as a function of this depth, and therefore the errors also accumulate as exponentially in n. Now there is a clever way, a more clever way to do this, and that's called a bucket brigade. So people who are familiar with bucket brigade is a way of dousing fires. Let's say if the fire is in the back of the room, for instance, then there will be a set of people who will channel a bucket of water starting from here to there, and therefore more efficiently, or with a chain of people, we can just transfer water to the end of this room. How does it work in the case of memories is that you give a register which specifies the address of the memory, and depending on each bit of the address, you either route right or left. So if the most significant bit is 1, then you route to the right. The middle significant bit is 0, you route to the left, and if the least significant bit is 1, you route again to the right. So in this way, by providing a binary input, you can access 1 bit of memory here if you provide it in superposition, and given these nodes or routers are quantum nodes, you could route or inquire about the data in superposition. Now how does it help is the circuit depth for such an operation reduces. So it's a linear function of the number of memory elements, and it has built-in error resilience. Now one way to see the error resilience of this system is that the error that happens here does not propagate to the other arms of the memory. So the error that happens at one level does not typically back propagate to the previous level, and therefore the other related graphs are undisturbed. So the question was, can we, and the error resilience, what it means for us is, the effective word here is that we do not need, so the makers of such an algorithm typically pitch it as it does not need error correction. So one good thing to test was whether the hardware characteristics dictate or inform us about whether error correction is needed or not. So one of our colleagues worked out the exact decomposition of such an operation on a superconducting system. There were other algorithmic decompositions available, but they did not conform with the native gates of a superconducting setup. So that was the first step. And it's not that he just worked out the circuit for this, but he also worked out the exact values of how many gates you would require, how would the circuit look like, and also an exact expression of how the fidelity would look like as a function of n, m, and the depth of the circuit. So this was one part of the work where people optimized in a way on the algorithmic layer. And this is how the circuit looks like for a bucket brigade QRAM. I'll not go into the specific details because of time. I'll jump on to adding the energetic or the energetic pipeline for this project. So we are now informed by the hardware as to how the algorithmic side of the circuit will look like. Now we want to discuss how would the energetic side look like, and therefore we move on to something called an MNR framework, which stands for metric, noise, and resource. So this is a framework which was introduced by Marco. He talked a lot about this in the morning, and others in this paper. And what it talks about is how does noise affect the metric of performance of a particular algorithm, of some application, of implementing a gate, and what are the kind of resources that you need to invest. And typically what underlies this kind of analysis is how efficient you are in performing a given task. So this at the quantum level can be visualized as an optimization problem, and that optimization problem is finding a set of optimal control parameters which affect the resource, the noise, and the metric of performance. So this is what happens on the circuit level, and we'll stick to this description. For our problem, we identify the relevant MNR parameters, and we talk about the control parameters that we have based on the superconducting architecture. So the noise here is the infidelity per gate. So once I have the circuit, I can say that every gate is noisy, and therefore the application as such, or the end-to-end circuit as such, will be noisy. The metric that we use here is the circuit fidelity, and the resource is by counting energy in terms of joules. So the objective can be written minimally in terms of optimizing the control parameters such that you are above a certain metric which is suitable for your application. So we adopt the specifics of the gate for superconducting qubit from Marcos and Alexia's and others' papers, and we can write the gate characteristics of these of implementing the algorithm on the superconducting platform. The obvious thing to see here is that there is a trade-off between the power that you have and the infidelity that you have, in the sense that if you increase the single qubit gate times, you will save on the power, but you will accumulate some infidelity for the gate. For the 2 qubit gates, we make some approximations relating with the single qubit gate, and we impose some kind of trade-off here by relating the infidelity of the 2 qubit gate with the power that you have to invest. So this is kind of an artificial model. So where does this calculation live? So it's not just that we are doing this quantum operation isolated perfectly well in a setup, that is the chip, but this chip itself is driven by a control line, and therefore you have this stack model where you have various attenuations and various cooling stages, and typically your control line moves from the room temperature to the cooling stage that you are at, and therefore once we are able to define the primitives of computation, we are able to say these are the native gates and this much energy they cost. We can define the dressed power consumption, which is basically a function of not just only the primitives of computation, but also the temperature, the attenuation, and so on. Now there is some physical insight into why this optimization is important and why should we consider such parameters. Is the Carnot factor that you see here, that defines how efficiently you can evacuate heat, means a lot in terms of if your fridge is operating at 70 Kelvin or 6 millikelvin. So for the same amount of heat, if you were to evacuate it at 6 millikelvin, it would be extremely costly as compared with something which is more near to the room temperature. So, and this delta A comes as a multiplicative factor. So if I were to allocate more attenuation here, that would mean that I do better on the noise scale, but that would also mean that I have to like spend extreme amounts of energy in order to evacuate the heat that I produce on this level. So this defines kind of trade-off between thermal noise and dissipation at cold stages. So let's define the optimization landscape, and we see there are a lot of control parameters. What are important to optimize, and at what time scales can we optimize them? So we fix a problem size, we fix a superconducting platform, characteristics of the superconducting platform, which are very optimistic in some way. As you see, the spontaneous emission rate is quite optimistic. So using the model for MNR combined with the optimization of the algorithm itself, that is the circuit, we are able to predict how would the average power look as a function of this parameter, which is the relative gate time and the gate duration, which is in nanoseconds here for single qubit gate. Now for 2 qubit gates, this defines how slow your 2 qubit gates are, and it also defines how noisy your 2 qubit gates are given everything else. So this is an experiment. It's a thought experiment per se, because the parameters are very optimistic, but this is to show that the methodology allows you to do optimization for power in like orders of magnitude level. So you could save, say, for 3 shades of green, you could save an order of magnitude of power and moving along a single line. So you could fix your fidelity. What you see here are ISO fidelity contours. So for 0.9, I could save like 5x the power, or almost an order of magnitude of power, if I switch from a regime which is like 75 nanoseconds to 25 nanoseconds, and correspondingly on the GFAC. So having detailed models of such algorithms allows us to do this multifaceted optimization. A more powerful approach is by allowing us to tune the attenuation themselves. So in a bit longer term goal, we might want to build a machine which actually allows us to do this kind of algorithms, and therefore we can also tune in some way we can tune in the attenuation, and we have considered 3 cases here. Now these cases are informed by, as I said, the trade-off between noise attenuation and the Carnot factor at lower levels or high levels of the stack. So if you're cold heavy, you have more attenuation in decibels, in dB, at the lower level of the stack, and this is costly. The plot that I show here now is for these cases of attenuation, and on the y-axis you have minimum power in order to achieve a certain fidelity here. So for a fidelity and configuration, you could find what is the minimum power I would require in order to achieve minimum average power I would require. Now you can do some more powerful analysis, and you can superimpose, or you can, because we have done such a fine-grained analysis, we can find power as a function of the circuit depth, that is as I do my operations, and this might impose some more constraints on the kind of power I can invest. So I might say that, okay, that's my maximum power, and therefore that will define the regime that I want to operate in. So this is the summary of an experiment that we did, and the parameters, as I said, are very optimistic. And what is the QE outlook for this work is QRAM is a universal bottleneck. It's used in many algorithms. Thousands of times it's called, and therefore one cannot neglect its energetic cost or the fidelity of such operations. Control parameter optimization can save a lot of power. Multi-constraint optimization, such as with maximum power, can be done. And this allows us to provide hardware roadmaps for useful QRAMs and feeds into MNR for quantum phase estimation. Okay, thank you. I'll leave with this slide.
So we have time for a couple of questions.
Yeah, thanks for the very nice talk. Maybe a silly question, but I didn't quite understand why you showed in some slide the power consumption as function of circuit depth. Why is it symmetric?
That's because the circuit is in that way. So it starts from, if we go back to the circuit, I can explain better probably. Okay. But it starts like how many routers you have to engage as you go deeper or to access the memory. And that's the reason.
Sorry, I didn't understand.
So you can do some simultaneous routing while, let's say, you are sending in one bit of information. In the meantime that it's going to reach or access the memory, you can do some intermediate routing.
Okay.
So that's why you can save some time, but it also leads to a fluctuation in the power while such operation is happening.
Okay, thanks.
So I have my skepticism, my skepticism on QRAM aside.
Yep.
How architecture agnostic is this methodology, QRAM architecture agnostic? Because we see a new one. We see several QRAM architectures popping up. You highlighted the bucket brigade, for instance.
Yes.
How agnostic is it to other architectures of QRAM?
Yeah, so one of the motivations for considering bucket brigade was that it has built-in error resilience. So we wanted to stick a number on the expected fidelities based on the hardware that we have got or projected hardware roadmaps. And so we looked at various other implementations, but this is why we can relate exactly the epsilon that happens in algorithmic side to the hardware epsilon that is expected. That's the motivation.
How resilient is this method to other QRAM architectures?
I think it's quite adaptable. So MNR is quite general in that sense. So once you have an optimized circuit which is close to what you would expect in a platform, you can build kind of models that use, and then you could have models which are more complex, like for solving QPE.
Okay, let's thank the speaker again, and the next one can head up. That'd be great.